All right, so yesterday we went over started section 1.2, an introduction to limits. We started off talking about how they were trying to introduce the idea of a tangent line, and knowing that a line required 2 points. One of the hardest things they were trying to do was to try to figure out how can you make a line that requires 2 points to be a line that only has 1 point. So they ended up saying, okay, we just got to get these 2 points closer and closer to each other. How close? Infinitely close, right? So we talked about that and came up with what we could call the slope of a secant line, which is right here. And using that, we found an equation for a secant line, which we learned in trig was called the difference quotient, right? So kind of just rewrote it there for us at that point. Now, from there, we moved on to example 1. And I basically gave you a function, which was f of x equal to x squared minus 4 over x minus 2. And what we ended up doing was we factored to try to figure out what this graph looked like. So we factored it out. We got f of x equal to x plus 2, but we still could not use x equal to 2 based on the problem. But when we graphed it, we noticed there had to be a gap there, right? There was a gap in this section right here, okay? So once we saw that, we realized, okay, the function does not have a value at 2, but does it have a limit, right? So we talked about limits last year, and one of the ways we figured out if it has a limit is we made a chart, right? And we tried to approach it from the left-hand side, right? So coming in this way, and then from the right-hand side as well. So we got our x values and made it approach from the left and the right, and that gave us these y values right here. And as you could see, the y values seem to be approaching the number 4. So that means as the x values got closer and closer to 2, the y values got closer and closer to 4. Okay? So that was our limit. So the way we write it is like that, right? The limit as x approaches 2 of f of x is equal to 4. Now, yesterday we did one more example, and it looked like this. Okay, find the limit as x approaches 3 of f of x if f of x is a piecewise function, which is x plus 2 when x is not 3, and 0 when x is 3. So we ended up graphing this thing. You can see it right there in red. It does have an actual point on the x-axis, right? 3, 0. So that point does exist here. And then it has a hole up towards the top. So one of the questions I asked is, what is f of 3? Well, by looking at the graph, you could see f of 3 was equal to 0. And then I asked, does a limit as x approaches 3 of f of x equal to 0? Because that's where the value is, right? It's right here. We can say, like, there's a value for it right there. So does it equal 0? No, it does not, okay? So what does it equal? Well, we have to look at where it's approaching. So as we look closer and closer, using those purple arrows there, you can see as you approach that empty spot from the left side and from the right side, the height that it's trying to achieve is a 5. Now, is it ever going to achieve it? Well, no, because theoretically, well, not theoretically, but realistically, there is no value there, right? There's just a hole. But theoretically, a limit doesn't need the point to actually be there. It's just going to basically tell you where it's supposed to be if it had the chance, right? This is where it's supposed to be. So it's supposed to try to reach this point right here, okay? And that point is 5, right? That's the height. So remember, limits are y values. So that's the height that it's trying to get to, okay? So knowing that, we were able to say that the limit as x approaches 3 of f of x is actually equal to 5, not equal to 0, okay? The real value is equal to 0, but the limit was equal to 5. And that's where we stopped, okay? But you don't always find limits for everything. So let me give you an example here. And we're going to graph the following. Find the limit as x approaches 0 of the absolute value of x over x. So we're just going to try to find that limit. So, I mean, I don't know if you know what this graph looks like, but just to kind of give you an idea of how I would approach this, not knowing exactly what I'm looking at. So I'm going to call this a 1. This would be negative 1. Here's 1, negative 1. So you got to think about this. Like, no matter what happens, whatever x value you pick, it's going to divide itself, right? So if you pick a 5, then it's going to be absolute value of 5 over 5. So that equals 1, right? If you pick a 10, absolute value of 10 over 10, that equals 1. What about if you pick like a negative 3? It'd be a negative 1, right? Negative 3. It's going to be 3 over negative 3, right? So negative 1. If you pick like a negative 20, it's going to be 20 over negative 20. So that's negative 1. So I can't pick a 0 because 0 is going to give me an undefined value, right? So what I got to think is, if x is greater than 0, then the absolute value of x over x will equal to 1. And if x is less than 0, then the absolute value of x over x will be negative 1. At 0, well, there's no answer there, right? I can't plug in a 0. I'm going to end up with a undefined term. So let me go ahead and graph this. So if x is greater than 0, I get 1. So it's going to look like this. And if x is less than 0, I get negative 1. It's going to look like that. Well, let's try something here. What would be the limit as x approaches 1 for this function? Think about that. Look at the graph. As x approaches 1, what's the limit for that? So I can draw it for you guys here. There's 1. Now pretend you're on opposite sides, colliding towards that line. What is the height? 1, right? The height's 1. So the limit to this would be 1. What about the limit as x approaches negative 1 of this function? It would be negative 1, right? So if you want, I can create these little things right there, right? As they crash towards each other from the left and the right side, you see that the height that they're going to be at is negative 1. So this limit would be negative 1. Okay? So, all right, let's go back to the original question. What about as you approach 0? Huh? Undefined, yeah. Now, how can I prove it? I got to show that the left and the right side limit don't match, right? So let me do that. Let me show that the left and the right sided limits do not match. Limit as x approaches 0 from the left side. So I'm going to show you guys some notation, okay? The minus sign as a power means left. A plus sign means right. Okay? So if I look from the left side, what does it look like it's going to from over here, coming this way? To negative 1, right? That's going to negative 1. where is it going from the right side? That's going to 1. Do they equal the same thing? No. If they don't match, if they're, what I'm basically showing here is that there's no collision, right? Those two arrows are supposed to be crashing into each other, okay? But they're not. Because if I draw the arrow up here, look, this green arrow right here, it's way up there. On the right side, it's coming in, it's going down, going up to 1. The other one's going to -1. They're not going to collide. There's no collision. So this is a does not exist. Okay, that's a DNE. Does not exist. Okay. So what about a graph that looked like this? What, just to see. What if I drew a graph that looked like this? Whoops, hold on. Give me a second. So I'm not going to draw any actual tick marks, just okay, this graph f of x, this is 1 over x. Actually, no, I'm wrong. That's -1 over x. Okay? If I ask what is the limit as x approaches 0 of this function, okay, what should I get? So I'm trying to get to 0, right? So let's ride the roller coaster here. Let's start from the left side, approaching 0. So notice, goes up, right? It's going up. What about if I come from the right side? That's going down. Are they going to crash into each other? No. So is there a limit? No. DNE, okay, does not exist. To find limits, a lot of times it's just eyeballing it. You're kind of looking and saying, like, is there going to be a collision? Because if they're going to miss each other, then there's no limit. But if they're going to crash, then there is a limit. Okay? So, all right, so there's that. Now, one more type of curve that you have to be aware of. I'm just looking really quick. By the way, those of you guys that are up here next to me, you're going to see I have these notes, and sometimes you see these big old X's. You see these big old X's here? It's because when I used to teach calculus many years ago, you guys needed to learn epsilon delta notation, which is kind of hard. But they would test you on the AP exam on this. But ever since 2007, they got rid of it. So I no longer have to teach it to you guys. So I have all these really good notes, but you can see big red X's, right? Because I don't need to go over that anymore. But that was more like theory. Like this was more like the stuff you learn in college. And they're like, no, we're not going to teach them that anymore. So I have like 4 pages of stuff that I wrote out for you guys, and none of it is useful anymore. It's useful in college, but not in high school. So anyway, let's do the very last thing. A graph that has oscillating behavior. Okay, so let me write this down here. Oscillating behavior. So I'll give you an example of this. Let me see if I can copy it over here. And then the middle is just going to look like this. Now you can, right now I'm going to give you the function so you could actually graph it on your own calculator if you want to, okay? So you don't see that I'm actually exaggerating. This function is sine of 1 over x, okay? So go ahead and graph it on your graphing calculator if you want so you can see that. So I'm not just making something up. Like this is actually what the graph is going to look like. Okay, it's a big old mess in the middle. Let's see, here's 1, 2, 3, 4, 5, 6. Okay, and -1, -2, -3, -4, -5, -6. Okay, so just because a function oscillates, a lot of people think, oh, oscillating function doesn't exist. Well, that's true and not true. An oscillating function could have a limit, but only in certain places. So, for example, if I were to ask you, what is the limit as x approaches 6 of this function, okay, what would you say if you kind of had to give it a guess? What would you say? They both crash at what height? About 0, right? You could say 0, right? It's a good guess. Maybe it's a little bit below, but it's okay. We'll just say about 0, right? We're going to say 0-ish, right? Because it's not exactly at 0, but we're just thinking about this out loud, right? So it's at about 0, okay? So here's the main question. What is the limit as x approaches 0? So in other words, right here, right, what is the limit? Well, where is it? Can you tell? No, right? We can't tell. We know it's between here to here, right? We know it's somewhere in there, but we don't know exactly when it's at any specific point, because once you get really close to 0, that thing is jumping up and down so fast. If you even try to get your calculator to trace it, it's just jumping everywhere, okay? So since it's nearly impossible for us to figure that out, then we say does not exist. Okay? So oscillating behavior of a function may or may not result in a DNE. It just depends on where they're asking you to evaluate it, okay? It doesn't necessarily have to be DNE all the time. If they're asking you what's the limit at -4, you should be able to figure it out, maybe like over here, maybe by plugging numbers in, making a chart, by maybe seeing that it's a perfect graph and you can literally tell where it's at. But you can find limits for different parts of this graph. You just may not be able to find limits for x approaching half, x approaching 0, okay, things like that, because the graph is just wildly uncontrollable in the middle. It's just jumping up and down, okay? Now you could say, well, it has a range. It's from like -2 to 2 or so. Your answer is between -2 to 2. But remember, limits doesn't want a range. It wants an actual height. Where actually is the height of this thing? And you can't really tell, okay? So when it comes to oscillating behavior, you're basically just going to decide, is it inside of the oscillating portion or is it on the outside? Because if it's on the outside, then I could probably figure it out. But if it's on the inside where it's going crazy, like a little Richter scale, right? Then, yeah, we're not going to do that one. Okay, we're just going to say, can't do it, and move on. All right? So that is the end of this section. I'm going to go ahead and stop the video, and I will give you guys your homework.